recording. Okay. So at the end of this class, we're going to be able to describe various types of waves. We're going to talk about like this thing called longitudinal wave versus transverse wave, and what that means, and how to quantify the properties and do a little drawing with it. And that way we can have a better intuitive understanding on how waves work and how to describe it. And that way we can actually do some fun stuff with waves and predict how they behave. So one kind of wave, we can actually see it here. It's actually known as a wave on a string. So here I brought a string so I can make a wave on a string. So in order to make a wave, you kind of have to tension it a little bit. So I'm not going to go back here, right? And the idea is that I'm not going to snap it or anything, okay? If you wiggle your arm up and down, right, it creates a little pulse of motion that goes back and forth, right? If I do it again, right, it's kind of bouncing back and forth. So this is known as a wave on a string, also known as a mechanical wave, okay? Because it's a mechanical motion that's causing this wave, okay? Here you have a little wave. This is actually known as a wave machine, where these two things are just kind of wiggling up and down to create the wave, just like, you know, I'm wiggling my arm in order to create the wave, right? But the machine actually is able to wiggle the wave at a particular frequency, so it's more precise and it can do it faster and doesn't get tired as quickly. Another type of wave is actually what you're listening to right now, right? The fact that I'm talking create these things called sound waves, right? It's not just a character on Transformer. Anyone watch Transformers? No, it's too old. It's too far back. Sorry. Soundwave was a character on Transformer. Soundwave is actually the wave that's, you know, I'm producing with my throat and my mouth, even through this silly mask, right? And then that wave gets propagated outward and then hits your ear. So I'm actually touching your ears with my sound, right? And then that gets into your earlobes, the inner ear, the eardrum, and then into the inner ear, and then actually gets detected by your brain as, you know, some sort of wave signal that your brain actually processes as words that I'm speaking to you. So I'd like to ask, like, besides mechanical waves or, you know, wave on a string and sound waves, what other waves do you guys think of? Is there any other waves that you guys can think of that you see? Light waves, right? Light itself is also a wave. This is actually known as electromagnetic wave. I'm not going to deal with this in this class too much because we're going to learn. So the next semester, you're going to learn about electricity and magnetism, and the combination of the two is actually what makes light. And we actually can figure out how it actually works. But the interesting thing is that the wave behavior or electromagnetic waves, it behaves the same way as sound waves and mechanical waves. They're all the same. They all obey the same set of rules. For example, like the speed of the wave, the wavelengths. We're going to talk about that, and then the frequency. What other waves can you guys think of besides electromagnetic waves, sound waves, mechanical waves, or wave on a string? Where else would you see waves? Where would you go? I'm sorry? The beach, exactly. So ocean waves, oops, is another type of wave, right? You know, I'm going to try to do a little crest here, right? Ocean waves is actually kind of complicated. It's actually a combination of multiple types of waves combined together, and it actually changes as it approaches the beach, as you see here, okay? And we actually get to examine a little bit of that in a deep area, not when it gets complicated when it hits the beach. Any other kind of waves that happens in California that you guys ever heard of? Anything that goes up? I'm sorry? Earthquakes. Yeah, exactly. Earthquakes are waves. Okay. Earthquakes also are waves. These are known as seismic waves. Okay. Right. And that actually, what are waves? Well, okay. So if you get deeper and deeper in the physics, what happens is that everything becomes a wave, basically, because if you actually take the third semester of this class, you learn about this thing called particle wave duality. So everything is a wave and a particle at the same time, but let's not talk about that. That's just going to be confusing for now, okay? So those are two, well, 1, 2, 3, 4, 5 examples of wave, right? And usually a lot of electromagnetic waves are actually different, a combination of waves that are multiple wavelengths. That's why when you have red light, it actually has a different wavelengths than blue light, right? And that's why we can actually see the different colors of these electromagnetic waves. But the combination of all of them combined together actually is what makes white light. And these wave behavior of lights, ocean, earthquakes, sound, string, right? All of them obey the same sets of rules, okay? And we're going to figure out how to describe it today in a little, just a quick quantification of it, okay? So in order to quantify it, what we're going to do is going to do a little bird situation. We have a little, I guess it's a seagull, right? That's sitting on the ocean, okay? And there's an ocean wave passing through that seagull, okay? So this wave, right, even though this is a picture, right, what's going to happen is that as this wave passes through the seagull, right, the seagull is going to rise with the level of the wave, right? So it just kind of bobs up and down, right? So I think a video of this would be better, but this is a decent picture also, okay? So what happened is that when the seagull is on the bottom, also known as the trough, this is known as the trough of the wave. It's kind of a weird word. I think it's like when you feed like animals, they eat out of the trough, right? Okay. When it's on the bottom, it's at the trough of the wave. When the seagull is on the top, okay, it's known as the peak of the wave. Okay, hopefully those make sense, like peak versus trough. Okay. The distance from this equilibrium point, right, is known as the amplitude. Right. This is actually, well, here is negative of the amplitude, but you get the sense of what the amplitude is, right? Right. We heard about amplitude when we did oscillation, right? So if you actually just, don't worry about the wave and just stare at the seagull, have a little narrow slit here, right? The seagull is up and down, going up and down, going up and down. It's actually executing a simple harmonic motion. A particular slice of a wave is actually just an oscillation, okay? But the difference is that, right, instead of oscillation, right, this peak of the wave actually travels to the right, okay? The speed that it travels is known as the wave velocity. Okay, hopefully that makes sense. Just how fast the wave is traveling. Okay. Okay. This one new thing that we're going to introduce to you for waves is that the distance from, let's say, this peak to this peak, right, is known as the wavelength. Because if you just cover this stuff up, let me just highlight the part of the wave that we want to stare at. Okay. This is exactly one period of a cosine function. Okay. Right. And the distance that between the peaks tells you what the wavelength is. Okay. You can actually measure this not just at the peak, but also at the trough. Okay. This distance at the trough is the same length, right? Okay. So the wavelength just tells you either the distance between the peaks, distance between the trough. Okay. It gets more complicated if you want to figure out the distance between at the 0 points, because you actually have to skip one, because in order for the wavelength is actually this long here, not this. This is actually only half the wavelength. Okay. So don't go from 0 to 0, right? 0 to 0 only gives you half the wavelength. Okay. Any questions so far? Just kind of very detailedly describing this little seagull on a wave. Okay. All right. There's one thing we can't see in here, right? is how long does it take for the seagull to go from the trough up to the top and back to the bottom, right? How long does that take, right? In oscillation, back in the previous chapter, right? When you have a, what was the oscillation we did, right? We had let's say a mass on a spring, right? And this thing is bobbing down and up, right, to negative A to positive A, and this is where the equilibrium point is, right? The amount of time it takes for this mass to go from negative A to positive A back to negative A is known as the period of oscillation. How long does it take for the motion to repeat itself, right? Same thing here. If we just look at the seagull here, we can also know what's known as the period of time it takes for the wave to repeat itself. Okay, how long does it take for it to repeat itself? Okay, so it's the same language as the oscillation. Okay, but in this case, right, instead of the oscillation just staying in one place, the wave actually moves forward. Okay, since the wave moves forward, well, let's just quantify these things just in case we forgot from last time. Okay, if you have the period of a wave, okay, if you want to figure out the frequency, okay, the frequency, which is the letter F, right, it's just 1 over the period. But if you want the angular frequency, right, you take the regular frequency, you multiply by 2 pi, right? So all these things that came from oscillation, the same symbols applies to waves, okay? The additional thing is that, well, I mean, oscillation doesn't have wavelength, so therefore we have to add wavelength. The other thing, since oscillation doesn't have, it's not, this little bobby thing is not moving forward, right? That means we also have to take into account the wave velocity. Okay, those are the 2 new things we're going to add to this. Okay, we're okay so far? It's a lot of variables. This is the thing when I remember taking this class. Like you have like lambda, you have V, you have ACE, you have F, you have T, you have omega, you have all this. You know, it's like a big laundry list of stuff. They're all like interconnected to each other, right? Right. Okay. Speaking of interconnected to each other, if you know the speed of the wave, I'm just trying to, is that like a vacuum going? Sorry. If you know the speed of the wave, I just want to double check I'm recording. Yeah. Okay. If you know the speed of the wave, you can actually relate that to the wavelength times the frequency. Okay. All right. No matter what the wave is, okay, it's always, just skip this middle part. This equation is easier because you know how I don't like fractions, right? Multiplication is a lot easier for me. Okay. If you want to figure out the speed of the wave, you just take the wavelength and you multiply by the frequency of that wave. And that's all you need to do to figure out how fast it's going. Okay. There's going to be other equations to figure out how we can actually measure this. But for now, for all waves, no matter what the wave is, you take the wavelength and you multiply by the frequency, you always get the speed of the wave, right? And now there's even more things to talk about, more new stuff. So remember this little string thing, right? What I did, right? I can't hold it up. I kind of wiggle my arm up and down, and that's what caused the wave to go forward, right? Okay. There's another way to do this, so but that I need someone to help me. Want to help? Yeah, just you may have to stand up. I don't want to hit the table. Okay. So the same way, I get this to kind of stay still, right? If I wiggle my arm up and down, right, you still get the same type of wave, right? Where it's an up and down wave. But the reason for the slinky, just hold on to it. Hold on to it. The reason I'm using a slinky, I can actually send a different type of wave. This is known as a longitudinal wave, right? Where the motion is actually along the direction of propagation. That's how I remember it. Longitudinal wave, it goes along the direction that the wave is traveling, right? You see that it's just the compression of the spring. It's kind of, you know, going back and forth, okay? As opposed to up and down, right? Which is a transverse wave. Thanks for your help. Oops. Okay. So the picture here shows you, right? Same thing here, where if the wave is propagating to the right, the motion of the slinky or the wave object itself is going up and down. It's transverse to it, or another word for perpendicular. I don't know why the mathematician decided to use two different words for the same thing. Okay, it's perpendicular to it. But if you have a wave traveling to right, but then the slinky is moving in this direction, back and forth, back and forth, back and forth like this, that's a longitudinal wave, okay? And this is actually kind of a cool demo of a transverse wave made of gummies. Okay, see how the volume is. Try to deafen everybody. You can hear that? Is there sound?
Yes.
Oh, there it goes. So these are actually just like gummy bears. Jelly babies, not gummy bears. You can make them out of gummy bears also, I think. I think it takes more than 5 minutes if you keep eating the gummy bears, though. I think I can fast forward through how he's building it. I just want to show you guys how the wave looks when it travels. Okay. Right. So all that motion up and down, right? That's a transverse wave, just like the string. Okay, so that's the amplitude, right?
Is the disturbance that goes from this end to the other. How does that work? Well, when I lift this jelly baby, it causes this bit of a tape twist, which twists the next bit, and so on along the whole length of the tape.
Yeah.
The twist that is moving through the tape. What the jelly babies do is add mass to the system and slow the whole thing down.
Okay, so one thing you want to mention is that there's mass on the jelly babies. That's why he had put the jelly babies there.
It transferred several meters along the machine by disturbance.
Okay.
Change the amplitude of the wave by simply lifting the jelly baby higher to begin with.
Okay, and it's gonna.
Now, notice that that doesn't change the speed.
Okay. And it's gonna.
If I jiggle the jelly baby up and down more quickly, if I or the shorter wavelength,
But still, notice that it's still going back and forth the same speed, right? It's not going faster.
And again, notice that that doesn't change the speed.
Sorry, he just said it, yeah.
You can change the speed of the but change the speed.
Okay. I don't know how many we're gonna watch him remove. Guess one at a time. Okay, he's done.
So, I removed the jelly baby from just over half the machine.
So watch this very carefully, right? The wave is same speed, and then on the right side is wiggling up and down a lot faster, right?
Is that as the wave cross the boundary from this part of the machine to this one, they speed up. Just like light waves speed up as they move from glass to air.
Okay.
There you have it. The wave machine.
So that's kind of like a nice demo, and then has to do with candy, which is good around lunchtime, right? But the main point that I want to learn from this is that you can have a transverse wave where the front is kind of like going up, and then the back is always going down, so they're always going opposite direction of each other. So you have a transverse motion still. It's still an up and down motion because the wave is propagating to the right, but then the motion is up and down, right? So that's still a transverse wave. Okay, and we're going to talk about this next next lecture when we actually figure out why does changing the mass on this particular wave system changes the speed of the wave, and we can actually figure that out. Okay, but for now, we want to do is just kind of quantify all these things that we just learned, right? So let's do a little quick example before we jump into the what's it called? The worksheet, right? So let's say we made we have a 30-meter long string. I don't think that's quite 30 meters. Maybe it's like half of that, okay? And the student holds it in one end and keep the tension on the rope, and then sends a wave down by moving one end of the wave up and down at a frequency of 2 hertz, okay? So as soon as you see these values here, right, you want to write down, okay, I'm going to write down that, well, the frequency is 2.00 hertz, right? Because the frequency is that F that we want, okay? The maximum displacement at the end of the string is 20 centimeters, okay? When someone say the maximum displacement of an up and down motion, what are they telling you? What variable are they telling you? The amplitude, yeah. So the amplitude, I'm going to convert that to metric, well, SI units, right? 0.2 meters, okay? Okay. The first wave hits the lab wall in 6 seconds. So that's like the amount of time it takes for the wave to travel across the room. Okay. Okay. And in fact, I missed some crucial information because they told us the distance that the wave has to travel, right? 30 meters, right? So if we were to draw this, right, this is the kind of like the x-axis, right? And the wave, right, is propagated forward with some speed v, right? It took 6 seconds to arrive, right? And the distance here, right, is 30 meters. That means the wave is actually traveling how fast? Okay. So we'll do the solution here, right? Part A, right? Part A asks you for the speed of the wave. Is there a way for us to figure out how fast is this wave traveling if it took 6 seconds for it to travel 30 meters, right? It's the speed, right? It's just the distance over time. So distance over delta t, right? You got 30 meters divided by 6 seconds, and therefore it's actually 5, well, that's 3 sig figs meters per second, right? So that's the speed of the wave, okay? What about the period of the wave? Period, right? This big capital T, how do we calculate the period with the stuff that's given up here somewhere? Which one will be the most useful? Sorry? The frequency, right? Because 1 over the frequency gives you the period, exactly. Okay, so this is 1 over 2 hertz. And I'm gonna write hertz in its base units, which is 1 over seconds, okay? Right, and that means it's 0.50. And since this is in the denominator of a denominator, that's an S, sorry about that, right? That becomes in the numerator, okay? So the period is half a second, okay? So part C, what is the wavelength of the wave? Okay, how do we figure out the wavelength? Any idea? Some sort of combination? Yeah, Jacob? Multiply the velocity, right? So the equation I want you guys to, well, that I like to memorize, let's just say that, right? The speed of the wave is always wavelength times the frequency, okay? That way I don't have to deal with fractions. If you know the period, there's also like, you know, this version of it, right? Where it's lambda over period, but you know, it's easier to just, that's the easiest for me to remember because I like multiplying things together as opposed to dividing, okay? So if we know the wavelength and if we know the frequency, right? Sorry, we don't know the wavelength. If we know the speed, we know the frequency, we can actually solve this for the wavelength. And therefore the wavelength is actually just the speed divided by the frequency, right? And therefore, the speed was 5.00 meters per second, and the frequency was 2 hertz, right? And so therefore, the wavelength is actually 2.50 meters, okay? All right. So speed of the wave has units of meters per second, as you expect. Period has units of seconds, right? wavelength is a length, right? So it should have units of meters, okay? Okay. So I think we'll save the other example for next time. But for now, let's just pass out the worksheet. Any questions while Ethan pass out the worksheet for us? Right. These are